Welcome to the 41st episode of the New Ventures podcast. I'm your host, Sanjoy Sanyal, the founder of Regain Paradise, a boutique climate firm, and a visiting fellow at the Cambridge Judge Business School. I host the New Ventures podcast to help people starting climate initiatives learn from others who are already progressed in their paths. Today, we're going to talk about green hydrogen. The Economist has called UK's hydrogen policy ambitious and a good starting point. As a part of implementing the policy, the government has awarded 22 companies with grants to produce hydrogen using bioenergy with carbon capture and storage. To understand how these grants can spur innovation in the hydrogen market, we have with us Ravinder Shan, the CEO of Phoebus Power, and his company is one of those which has won this award. Ravinder, welcome to the podcast.
Thank you, Sanjoy.
Ravinder, your project, as I said, is in the broad area of producing hydrogen with bioenergy and carbon capture and storage. I think we should start by just explaining this word a little bit.
Yeah, green hydrogen by definition means that generation of hydrogen through zero emissions. So anything that does that is called green hydrogen. Hydrogen per se, production of hydrogen is so many different colors today that people often get confused. So there is green, there is blue, there is turquoise, there's so many different colors. But green hydrogen is what we are focusing on because it helps UK achieve its net zero ambitions. And just because it is zero emissions, it helps them move towards a cleaner and a better society as well. Now, predominantly, when we talk green hydrogen, people think from solar or from wind, but there are other sources as well. And bioenergy or biomass is one of the most prominent ones. The reason being that it is available today. A lot of it is going for waste, or some of it goes into biomass plants where they burn it or gasify it. Now, strangely enough, these plants also emit carbon dioxide. So they're not really, helping the environment. But because this is biomass and it absorbs carbon dioxide, and when it emits it, this is still considered net zero. Now, what is different with us is what we are doing is taking this biomass, generating hydrogen, and whatever carbon dioxide is emitted, we capture it again. So in reality, we are actually decreasing emissions in the environment. And this is a very important differentiator between this program, which is called H2B CCS, which stands for hydrogen from bioenergy with carbon capture and storage. Because this is really the first program where it is all about not just zero emissions, but reducing the emissions in the industry. And this is very important because there will be so many other industries where there will be emissions. So if we need to get to net zero, programs like these are very important. Now, what is hydrogen from bioenergy? What does it mean? Very simply, bioenergy or biomass, it consists of carbon, hydrogen, and oxygen. These three are the main components. Typically, it's in the form of glucose or cellulose. So what we do is we break this carbon, hydrogen, and oxygen bonds to take out hydrogen, and then there is carbon dioxide or CO2 left, which is again captured in our process to actually help improve the production of hydrogen. And I'll go into those details later on. But this is what the program is all about, is looking at innovative technologies to produce hydrogen from biomass.
Right. And I was reading the policy of the UK government, and the UK government actually, in its policy modeling, it puts more emphasis on things that you talked about, which is producing hydrogen from electrolytic production using renewable energy, or introducing carbon capture and storage in existing processes which involve methane. But yet, at the same time, they have given out 22 grants in this area, which policy does not really feel could be important. I think, therefore, they're taking a serious bet on negative emissions, is it?
Yeah, I think that's one aspect. But if you look at why from biomass, from a UK point of view, look, solar and wind, yes, they are good sources of renewable energy. And producing hydrogen from electrolytic processes is kind of being proven now. And a lot of projects world over are being set up to scale these. But UK is not a great source of solar, and wind is also limited in certain areas. and it takes a long time to develop wind power projects. So if UK needs to get to and meet its decarbonization goals, hydrogen is definitely one important piece of it. But how do they produce a lot of hydrogen if they don't have enough solar resource and wind? And make sure that it is zero carbon as well. So that's where biomass comes in. And there is a lot of biomass availability in UK. As I mentioned, part of it is also being used in biomass power plants. So there are opportunities where there have been benchmark studies done on biomass to hydrogen by UK government itself. And they have realized that the opportunity to get to the lowest cost of hydrogen is actually with biomass. So that's where this initiative is, it's all about, is that can we find some innovative technologies, help them with the initial stages of development so that they can reach commercialization in the next 2 to 3 years. And that's when large scale deployment of these technologies happen and we get to the lowest cost of hydrogen. Just to give you an example, our initial estimates, and we do work on solar to generate green hydrogen as well, are about 7 to 8 pounds per kg for hydrogen if we do from solar electrolytic. This would in next 2 years. We are looking at biomass to do the same thing, hydrogen production around less than 3 pounds per kg. So less than half of what is possible with solar in the UK. So that's where there is a huge potential to do this. And that's why this interest. But all of these technologies are in early stages. So we need government grants to actually do the feasibilities, come up with the right model and implementation strategies for demonstration projects. And the next phase is to get the grant for demonstration projects and then get to commercialization in 2 years.
And these 22 projects are in 3 areas, right? Feedback processing, gasification components, novel biohydrogen technologies. You'll have to explain these words to our audience, just using perhaps words that a high school student would understand.
Sure. So traditionally, all biomass to energy pathway world over and UK as well is gasification of biomass to produce syngas, which is actually used then to power plants or used for heating purposes. Now, syngas is nothing but carbon monoxide and hydrogen. And so this is a pathway which has been followed. It still exists. Most of biomass actually that is being used in UK goes to gasifier plants to do this. So there is a possibility to then extract from this syngas, which is a mixture of carbon monoxide and hydrogen, is to take the hydrogen out and through water shift, convert carbon monoxide to carbon dioxide and capture it. So that's one part of it, which is actually forms a part of category 2 called the gasification. Now, the feedstock for this gasification is the biomass, and how can you process it so that it can provide the right amount of syngas, which is carbon monoxide and hydrogen, and the mix should be such that the hydrogen production is maximized. So that's where the category 1 is, which is feedstock pre-processing. So these two categories, category 1 and category 2, are kind of related to each other and supplement each other. That first one focuses on processing of feedstock so that it can go into gasifier plants to maximize hydrogen production. And the second one is to improve the gasification processes. One is for the separation of carbon monoxide and hydrogen, and also to ensure that there is a process to capture carbon dioxide. And the third category, which is where we won the grant, is the novel biohydrogen technologies. Now, within novel biohydrogen technologies, there are quite a few different ones which do not involve gasification. Gasification, just to explain, is basically heating up the biomass in the absence of oxygen. And you heat it to a certain temperature where it breaks. As I mentioned, there are bonds of carbon, hydrogen, and oxygen. So you heat it at very high temperature to break these bonds, and that's gasification. So our category 3, which focuses on novel biohydrogen technologies, within this, we are focusing on a very unique process, actually never been done on a commercial scale, which is taking this biomass and putting it through dark fermentation. Basically, by definition, is fermentation process in the absence of light, and doing this anaerobic process to generate part of hydrogen. We think about 15 to 20% hydrogen, and then rest is in the form of a slurry. This slurry then we take into a next process called photofermentation, which by definition, photo is in the presence of light, and we do the fermentation process in the presence of light. And here again, we generate about 45 to 50% of the hydrogen. And the rest is all again slurries, which can be then refined to produce fertilizers. It's called digestate, but it's very rich in compounds which can help soil growth. So this is our novel biohydrogen technology. We think there is a huge potential here to do this. And then any carbon dioxide that is generated in this process, we take it and put it through a proprietary process to actually generate more algae, which is again used in the process of dark fermentation. So it's a closed loop process of carbon dioxide capture. And we think we can capture about 95% of the carbon dioxide in this process, eventually get to 100% hydrogen production from this process. So those are the three categories. But for us, it's the category 3, which is the novel biohydrogen technologies. There we are.
Well, you've done a fantastic job. Obviously, there are other novel biohydrogen technologies on which grants have been given, but the one that you are talking about is obviously very interesting. Before we go to the next section, where we will understand more about what exactly you're doing and build upon what you've already said, let me quickly summarize some of the important points that you made. First point that you made is for UK to reach its net zero goals, green hydrogen is obviously going to be very important to decarbonize broad sectors of the economy, heating, transportation, and then, of course, industrial production as well. And there are methods that are being put in place for making green hydrogen. One is using electrolytic production, using renewable energy, and, of course, using carbon capture and storage in existing processes of manufacturing hydrogen. Important thing about producing hydrogen with bioenergy, along with carbon capture and storage, is that from what I'm taking away is two things. One is that it is actually negative emissions because the biomass actually absorbs carbon dioxide in the first place. This has already been there in the UK. So the UK does have biomass plants. But the other thing that you mentioned, and which is, I think, important, is that early modeling shows that this could be actually cheaper than, let's say, the electrolytic production of hydrogen using renewable energy, almost half the price. But obviously, these technologies are in early stage and therefore need grants to be demonstrated and scaled up, which is what you're doing. And these grants given out by the UK government are, one is around improving the gasification, which is improving the warming up process to produce more hydrogen. And of course, having the necessary feedstock to be able to be used in these gasification technologies. And the other is, of course, in completely new ways of manufacturing green hydrogen. In your case, it is using fermentation, first without light and then with light, but to produce, for very high conversion rates is what I'm taking away so far. Is that a reasonable summary?
Yeah, I think you did a great job of summarizing, definitely.
This is such an interesting topic. So we move to the next section, then we'll try and build on this. We've already explained what you're going to do with the grant. And obviously, my first question is, who are your partners?
Yeah, so we have partnered with Grassroots Energy Technology, which is a company that focuses on these fermentation and digestion processes. So traditionally, biomass is also being used in UK and world over is in AD plants or anaerobic digestion plants to produce biogas. And biogas is nothing but predominantly methane, but some other gases as well. And Grassroots actually focuses on production of biomethane. And then they've got few projects around this all over the world, specifically in India. Now, what we do is we use the same digestion process, but with some proprietary improvements and enhancements and changes to produce and to also condition these bacteria which are used in fermentation to produce hydrogen instead of methane. So that was the interesting and novel part of this technology, where Grassroots had done quite a bit of work, have some patents around it as well. All of these are at laboratory scale. So we chose them and we partnered with them to help us actually develop this further. And then our second partner in this is our laboratory partner, which is Newcastle University. Newcastle University has a lab which is dedicated to these bioengineering aspects, and we are working with them very closely. In addition, they also have a chemical engineering department, which can provide all the laboratory testing facilities and also help us in developing a small pilot, which we can later on scale as a demonstration project. So these are our two partners. One of the additional benefits I'll mention here with Newcastle University is that they also do farming on almost 800 hectares. So they have availability to all kinds of feedstocks that we will need for testing of these technologies that we are developing with grassroots.
Right. And then with this particular grant, what are you trying to achieve?
So we have quite a few objectives. A major objective is to actually develop a feasibility study for demonstrating this technology at scale. Currently, as I said, there is no commercial project. It has been attempted on laboratory levels. There are enough studies to show that, yes, it is possible to do this, to produce hydrogen through this biphasic process from different biomass feedstocks. Currently, the yields are around 1% at laboratory level. Theoretical yield is about 16%. So our goal is to get to 2.5-3% by the end of this. So you can imagine that there are certain enhancements and improvements that we are doing through this grant and through the laboratory tests that we are doing, that we get to this. And the end of this grant, our intent is to have a complete study which showcases what do we need to do to set up a demonstration project, which is a phase 2 of this grant, where all the 22 projects which have been chosen will be eligible to apply for the phase 2, where 2 to 3 projects will be selected. So our intent with this grant is to actually develop the model which could help us in going into the phase 2. Now, go a little bit more detail, what we are doing is there are many different kinds of biomass available. So one aspect that we want to do is identify what biomass provides what kind of yield. And eventually, we foresee in the future that we will be blending different biomass feedstocks to get to the right mix. And all these feedstocks are very geographically dispersed all across UK. And our model is not to set up one project. Our model is, and the advantage of our model also is that it can be distributed. So rather than setting one big project in one place, we can be distributed all across UK, very near the sources of consumption, and set up these projects. So we are already thinking of commercialization of these projects when we are doing these feasibility studies. We've chosen 4 feedstocks. One is the straw, which is coming from wheat or barley or oat. So it's an agri waste. The second is energy crops, which this is also a major initiative of UK government, where they are growing miscanthus or SRC willow. And these energy crops are again going into these biomass plants that I talked about. Third is the food waste, which also we generate quite a bit in UK, and to look at the food waste. And the fourth is grass, herbal lays. And UK has a lot of grassland, which is actually currently a huge potential to produce energy as well. So these 4 feedstocks we are testing. And then what we are doing is we are developing a design for the bioreactors, both the dark fermentation and the photofermentation bioreactors that can be developed on scale for the phase 2 demonstration project. So we are developing these designs currently and testing them on a very small laboratory scale. And based on our data and based on our experiments, we'll be able to design what kind of reactors we need for the demonstration project. So these are the major initiatives of this, what we intend to do with this grant.
This is, again, very, very interesting. I'll pick up on several things which you already said. But one of the things that I am immediately thinking about is that this movement from 1% to 2%, and then the demonstration project that you would be doing, will the demonstration project at commercial level, or it will not be?
Just to give you a size, so right now at the laboratory level, we are testing feedstocks in grams and kilograms. And what we are thinking of going in the demonstration project is somewhere between 10 tons to 20 tons per day of feedstock product, which will go as input into this biomass. So there is a scale that is going to happen on the demonstration project side. But the experiments on the laboratory level are very important for us to figure out the right parameters, right design criteria, and the right feedstocks that we need to go for this demonstration project.
Right. From the 20-ton use of biomass in the demonstration project, the amount of hydrogen that will be produced, will it need to be stored or distributed, or how will it be used?
Yes. So for us, it's very important to choose a site where we can actually utilize this hydrogen. So that's where we have chosen one of the farms, which is managed and owned by Newcastle University. They already have quite a bit of infrastructure there. So they will need the heat, they'll need the energy, the electricity as well. So we are still working on the design of how and what can be consumed on site. But the intent is to set up something like a CHP, a combined heat and power unit to run the farm. So provide the heat and electricity to the farm. And if there is any excess electricity, we can always put it back into the grid. And the second is, if there is excess hydrogen, we might just store and ship it to Newcastle City, which is very near this. I think it's about 15 to 20 miles. And in all the major cities in UK are actually planning hydrogen for mobility, so hydrogen buses. And so this is where this can be utilized as well. So 20 tons, we are thinking we can produce, I would say, about 600 kgs of hydrogen per day. So it's not a huge production if you look at manufacturing units, and I'll talk more about what we plan to do in future. Requires about few tons, from few tons to few hundred tons per day of hydrogen to meet their requirements. This is a very small production unit compared to commercial scale, but this will give us enough idea on what do we need to do to get to commercial scale in 2 years, 3 years time.
Right, which is why you're calling it a demonstration project. Today is a feasibility study, demonstration project, and then commercial study. We'll obviously have to talk a little bit about the different types of feedstock that you're targeting. And I think the grass is obviously very important. The UK has a great tradition of commons, land area that is accessible to anybody. And one of UK's greatest traditions, I must say, is, of course, the park run concept. Every Saturday at 9 o'clock, people run the commons. Everybody understands that. What people will start questioning is about this energy plants, because everybody is going to be worried about early 2000s, right? When there was a lot of conversion of land that was available for food for energy crops, especially as we go into a cost of living crisis.
Yeah, no, I think that's a very good point, because I think a lot of it is perception versus what is reality. Let me take one by one, and then I'll go a little bit more into what is next in terms of feedstocks, which will give you a good context of why we are starting here. First, which is straw. And straw is all agri-waste. If you need to produce wheat, there will be wheat straw. If you need to produce oat, there will be oat straw. Barley, there will be barley straw. So the more we produce wheat, the more straw would be there. And it's in our interest that we actually increase farmland to do this. And today we produce about 11 to 12 million tons of straw per year in UK. Most of this straw goes into different applications, but a lot of it goes into these biomass plants where they burn it to generate carbon dioxide. We are talking of taking this straw, instead of generating carbon dioxide, actually reducing it. That's one area. The other is, a lot of it again also goes for animal bedding, where they use it for animal bedding. And then once it is done, this again actually goes into landfills. So we are talking of taking this animal bedding, which is actually a very good source for us, and using it. So our focus is with straw is to really focus on things which are actually now currently being used for applications which are harmful for the environment. So take them, there is enough availability, and increase farmland as well. So that the perception that we will be decreasing farmland actually is not true. Now, the second one, which is energy crops. Now, this is where a lot of controversy has happened over the years. And reality is that energy crops, again, are today being used by the biomass plants. Actually, more than 70-80% of the energy crops today grown, which is miscanthus and willow, go into this biomass plants. Some go into the biofuels, biodiesel and those. But there is a huge initiative by UK government to increase the land area of energy crops, because whatever we use in terms of energy crops, it helps us reducing our dependence on external oil and external gas, which we are seeing right now is how it is affecting the prices in UK. So a lot of these, and I think the total grant was about 10 to 15 million pounds have been awarded in last few months to help companies scale up energy crops. Of course, they have to scale up in such a way that they don't harm the environment and they don't decrease the farmland. So there is a lot of land available, but farmers don't crop anything because there is not enough revenue. So, but with the energy crops, they provide a very good revenue. So there is initiative by UK government to increase this energy crops. And currently it's only about 0.1% or 2% of land. So it's not huge, but there is initiative to do this. Then the third feedstock is food waste. Give you an idea, UK does about 60 million tons of food every year, and about 13 million tons of that is wasted every year. A lot of this food waste ends in landfills. This is where we need to get better. Some of this food waste goes into AD plants, where they again use it to generate methane. And our initiative also is we are looking very closely to at these AD plants. There are about 40 of so in UK, anaerobic digestion plants. And we can easily retrofit them that instead of methane, they produce hydrogen, because we are using very similar processes, just a difference in reactors. So that is something we will look at in the future, where we use these plants to generate hydrogen. Now, why hydrogen instead of methane? Methane is basically natural gas for you. If you burn it, you generate carbon dioxide. But hydrogen, when you burn, you generate water. So there is water vapor. So it is much less harmful, or actually it's not harmful for the environment at all, burning hydrogen compared to burning natural gas or methane. So having a technology to actually retrofit these plants in future to produce hydrogen instead of methane is also a very big opportunity that we are looking at. And then the fourth is grass, which is another huge opportunity currently untapped. There is about 6 million hectare of grassland in UK, potential to produce 2 to 3 million tons of grass, which can be used for bioenergy purposes. Most of grass is currently being used just for animal grazing, which can continue. We actually want to increase, but a lot of it just grows and there is no maintenance. There's nothing. It's just they cut it and it goes to waste back into the landfill. So this is again an area we are looking at closely. To reiterate, all these four feedstocks that we have chosen today are by design, because we think there is a lot of wastage that still happens. And what we want to do is utilize this waste and create a model where a lot of this waste, instead of going into technologies which are generating carbon dioxide or going into landfills, we are able to generate hydrogen, which is essential for our energy requirements and also for decarbonization.
I think this is an adequate explanation. And another thing that I wanted to pick up a little bit on is this point that you made about these plants being distributed. To me, obviously, again, we're not there yet. You will get through this phase, then you will get through demonstration phase, and then you'll get there. But, we are all optimists. And if we get to a point where you can actually locate these plants all over the United Kingdom, what would this mean for the heartland of the country?
So let me explain what I mean by distributed. One of the biggest challenges with hydrogen is transportation. Hydrogen is the lightest molecule. In terms of volume, it's not energy dense. In terms of weight, it is. So if you have to store hydrogen, you need to really compress it to very high temperatures. If you want to transport it, you either need to make it into a liquid hydrogen, which again requires very low temperatures, almost minus 200 degrees Celsius in high pressures, or you need to convert it into other carriers like ammonia. Now, if you look at biomass is also a carrier of hydrogen, and it's easier to transport biomass than to transport hydrogen. And even today, if you look at these biomass plants, biomass produced in south of England travels all across England to north to go to these biomass plants where it is burnt and generate CO2. So one of the things that we really want to focus on is that optimal utilization of biomass. It is being produced all over the country. That's why these different feedstocks, having these kind of collection points near where each kind of biomass is being produced or is available in volume. But more importantly, we want to be distributed because we want to be near the consumption points. Now, consumption points today could be these natural gas substations, which are all across UK, and they are already experimenting, some of the natural gas operators, on adding hydrogen to it. And today, the system can take about 10 to 15% of hydrogen. You can easily add, which is basically, reducing your natural gas emissions by 10 to 15%. But the other area, which is very, very important for us, is the industry. Industry is one of the most difficult sectors to decarbonize. And I mean industry which is energy intensive and heat intensive. Industry that requires a lot of heat for its manufacturing process. So we are talking of steel industry, we are talking of paper industry. There are about 12, 13 different kinds of industries which have been earmarked by UK government where they need to decarbonize. But the only option for them to decarbonize is to do away with natural gas. And for that, hydrogen is the best alternative. So this is where we are thinking to be near the industries, near the consumption points. And our footprint is not very big with these. I think our ideal size would be 50 to 100 tons per day of feedstock, which can be easily available for us in different geographies. And we'll be very near these consumption points, providing hydrogen directly to the consumer. Additionally, UK government is also planning hydrogen pipelines around industrial areas. There are quite a few programs that have been announced, HyNet being one of them, Thames Estuary is another, where we can also be near these hydrogen pipelines and just pump hydrogen directly into them. So there are different consumption points and possible injection points. That's why we need to be distributed. If we cite one large project of 1,000 tons per day in one area, then we will be transporting hydrogen, which is much more energy intensive because we'll have to pressurize it, reduce the temperature, and will be very expensive to transport as well. So that's where the distribution becomes important.
I think we've understood some amount of detail what you're trying to do and how it will really help if you succeed. And of course, the very best wishes. Before we go to the next section, I just want to ask you one question. It isn't easy to put in a grant application and win it when you have three partners and you have a university and then you have another organization which is doing its own thing. How long does this process of putting together an idea that will really work? Just give us an insight into that process.
Yeah, grants are difficult. It requires a lot of work. And I think the will to do this and the belief that this is very important for us, for the country and for the environment, kind of pushed us to come together. And all three stakeholders, ourselves, grassroots and Newcastle, really believe that producing hydrogen from biomass is one of the major opportunities and also, one of the opportunities which can lead us to the lowest cost of hydrogen in UK. So I think that kind of aligned us, and we spent quite a bit of time developing our grant application. But the idea was there in our mind. We knew we wanted to do it last year. It took us a couple of months to put together the grant application, but the concept and the thought had been there for a couple of years to do this. So that's what brought us together. I think one point, if I may mention, and which is what's next for this technology, which is also an important point to put in context. And we will be working on grants for that as well, which is that once we understand that we can produce hydrogen economically from biomass, we need to look at where else the biomass is coming from, where else is there a biomass waste. And we have already done quite a bit of work. We are going to start that next year, which is with the paper industry. Now, just to give you an example, paper industry also produces a lot of paper sludge. It's sometimes called paper crumble, which is also nothing but cellulose biomass. It is interesting to know that most of them are actually paying money to either remove this from their site because it's a part of the water they need to, for effluent purposes, they need clean water. They are setting up plants, anaerobic digestion plants, where the water is being cleaned, but nothing has been recovered in terms of methane or biogas or anything. Some plants are recovering biomethane, but it's only in such small quantities, it only meets 2-3% of their energy needs. So we've done some initial analysis for paper sludge as well, and we think we can meet 15% of the energy needs of this industry from the waste that they produce. Now, if you imagine 15% of your energy needs coming from the waste which you are actually paying to remove, it's a huge benefit. And then on top of that, this feasibility study tells us which biomass we can help us enhance hydrogen. Our intention is, as we move forward, is to combine paper sludge and other biomass as well, and to move to a scale where we can meet 30 to 40% of the needs of the paper industry, which is a hugely energy intensive industry, where it becomes sort of a closed loop system because it's their waste, which again goes into generating energy for them. And this is one industry. Same thing happens with food and beverage industry. Same thing happens with sugar industry. So there are a lot of industries which generate biomass waste. And that's another area that is the next step for us and was. So this grant application is the first step for us. There are many more areas where we think there is a potential, and we will be looking for grant applications to develop that. And that's the reason to keep on working on this and developing this so that we can get to a point. There is a huge potential. Just to give you numbers, paper industry globally, it's about 400 million tons of paper. And our estimate is about 4 to 5 million tons of paper sludge is generated every year. And if I just look at the hydrogen potential, it's about 5 to 6 billion pounds per year. So there is a huge potential just from one industry. You can imagine in terms of what it can do if we start adding industries and different feedstocks. So these are things that excite us. I think that's where we were ready to put in the hard work, and we are working towards more grants as well.
It is definitely exciting me, and I hope it'll excite our audience as well. We will move to the last section where we will talk a little bit about what prompted you to start this business and about your background. But before that, let me just kind of quickly summarize what we have learned so far. What you're going to do with this project, as you said, is do a feasibility study, which is at the lab level. What type of reactors, I suppose, reaction parameters and so on and so forth. And you're going to do this with a company which has been working on anaerobic digestion, but instead of using anaerobic digestion, for our audience, obviously, is digestion without oxygen, but instead of producing methane, it will produce hydrogen. And you already mentioned the problems of methane. One of the things that I should say, and we had in our podcast, a company called Kerus, which actually tracks methane production and leaks all over the world. And methane is far more potent warming potential than carbon dioxide. That's very important. The other thing that you'll do, really speaking, is that you will experiment with 4 different types of feedstock. In the philosophy of testing with feedstock, I think the philosophy that I'm hearing is increasing farmland and at the same time reducing waste that lands up in landfill or is just not useful at all. The UK obviously has a great potential for reducing food waste, like any developed economy, but there's also, just because of the societal traditions, has a long tradition of having the commons, which can produce grass, which can be used as feedstock. And the last thing that I'm hearing you say is that if all goes well, you can actually place these plants, or sort of dot these plants all over the country, near consuming centers, but near producing centers as well. And to me, that point that you made about being able to decarbonize industries which use a lot of power, like paper is the one that you described in detail, is also, in my opinion, going to get jobs back to the UK. And it's also part of the leveling up of UK's heartland. These are obviously hopes and aspirations. Well, I think this, hearing you speak, there is obviously a real opportunity to do this. Is that, again, a decent summary of the last 15 minutes or so?
Great job, Sanjay.
Ravinder, I have to ask you actually that Phoebus Power, has been the company you're CEO of, has been in business for 4 years. And it has a business before green hydrogen, which we talked so much about. Can you please explain what all have you been doing?
Yeah, interestingly, Phoebus Power, I set it up in 2019, and our focus initially was to help companies transition from their existing energy infrastructure, which emits a lot of emissions, to this low carbon energy technologies and help them move towards net zero. So I work closely with a couple of companies, some of the large energy brokers, which have huge client base. And so Phoebus Power works with them and helping them move to solar and combined heat and power and other energy efficiency technologies. And so this was our initial initiative, and we've been doing that. And additionally, we partnered with a company called Tyler Hill and helping develop these distributed solar solutions. Tyler Hill also does large-scale solar projects. This was the initiative. But in last couple of years or so, we've become very focused on hydrogen. And this is now the new direction of Phoebus. I'm still involved with Tyler Hill and I have some other initiatives. But as a company, Phoebus is becoming more focused now on hydrogen moving forward. But then our other initiatives with Tyler Hill, and we've just partnered with another company, large global IPP called FRV, to build battery storage projects in UK. Phoebus has become now looking into different and novel ways of developing hydrogen for the UK industrial economy.
So, Ravinder, I'm glad that you mentioned Tyler Hill Renewables. I was looking at their website, and is grid-connected projects their main focus? And if you can tell us a little bit more about the types of grid-connected projects they have done. And I'm always curious to know who are the types of investors in these projects.
So with Tyler Hill, I'm one of the members of Tyler Hill management team as well. We are looking at distributed solar as well as utility scale solar projects. So we are doing that for quite a few of clients. Then additionally, we have partnered with FRV, which is a large global IPP. And together we've formed this company, FRV TH Power Tech, to focus on utility scale battery storage projects in UK. As you're aware, we are moving towards energy infrastructure, which is more focused on solar and wind as coal plants are shut down and as even gas plants are phased out eventually. Now, solar and wind being very intermittent, sources of generation compared to coal or natural gas, where the plants could run 24 hours. Sun shines only during the day, so that's when solar produces. Wind is available at certain points during the day or especially in the night, and that's when wind power plants produce. So this intermittency creates a lot of instability, and that's where storage becomes very important. Now, today, storage industry is predominantly focused on battery storage for short term. And then for long term, we have technologies like hydropower, etc. We've started with battery storage, but eventually we even see a hydrogen playing a role in this, because hydrogen can also be stored and can be used at times and can provide long durations, sometimes even for days energy. So this is something very interesting as well for us to look forward to in the future.
Great. I'll be coming to the end of the podcast, and I have to say, you moved to the UK. When did you move to the UK? And it looks like some of your colleagues also did. And one thing that I was thinking about your background, and there is something about the UK which attracts innovation talent in the climate field, isn't it?
Yeah, absolutely. I moved to UK 2018. Though I've been coming here for a while. I was in US also for 10 years. That's where I started my clean tech journey. Moved to India again to set up a solar company there in India, and then eventually moved here. Though I moved here more for personal reasons, but the major factor in attraction was for clean energy entrepreneurs, UK is certainly one of the places to be. Whatever the government might be, has always had a very climate friendly approach in its policies and has a very good infrastructure and also talent that we can look at in terms of helping us building really good companies here. So this is something, which helped us very easily to come. And then on top of that, the grant infrastructure towards doing something novel. I have not seen any other country having a hydrogen from bioenergy grant program. So this is again very interesting for us because most of the world is still focused on solar or wind for green hydrogen. But there are other avenues which can be better. So that's also something which is a huge plus point of being in UK.
Yeah, absolutely. I think as Indians, both you and me, we have to say that we have contributed to the UK society with its chicken tikka and its curries. And we do have to contribute to its climate technology businesses as well. Jokes apart, I mean, one of the things that I feel very positive about the way you say things, and I was looking at the other grant winners as well, many of them have tie-ups with universities. To me, that says something. This is, to me, very critical in the climate transition, this research and industry, and especially entrepreneurial industry linkages.
Yes, absolutely. I think universities is another, and the way we've seen with Newcastle, and we've worked with other universities as well in the past, they are also as keen as us to do this. They are also very keen to help us in terms of commercialization. A lot of times universities are think of R&D and they think more on research papers and all of that. But I've seen a lot of these universities are thinking on how can these entrepreneurs commercialize and how can they help us in doing this? And that actually is very much aligned with why would we want to work with universities is that they believe in this. They believe that working on these technologies and then commercialization of these is the way to go. And they have put their resources behind it. So that's something definitely it's a credit to the system here and to the universities in UK.
And with that, any final thoughts? And if people want to get in touch with you, how should they?
I'm available. People can always reach out to me through LinkedIn or through our company website. And, happy to chat with anyone and be in touch with anyone who is interested in this sector. For us, both hydrogen and clean energy are some areas, that we know we will always be very keen to collaborate and partner with others. So always looking forward to talking with like-minded individuals. So please do reach out. And I'm always open to learning from others as well.
That's a very nice thing for you to say, Ravinder. With that, thank you very much, Ravinder. It was wonderful.
Thank you, Sanjay. Thank you for having me.